Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video dealing with the lab exercise Modelling Precambrian Surface Conditions. So we're going to move on to question 2. And question 2 postulates, well, what's going to happen if we keep pumping greenhouse gases into our atmosphere? It's obviously going to increase the Earth's greenhouse effect. I do appreciate for some people this is a controversial idea, but the scientific studies that have been conducted to date show, yes, global warming is taking place. It is real. So if we keep pumping greenhouse gases into our atmosphere, and let's say it doubles the intensity of our greenhouse effect, so it takes the greenhouse effect to 2, what is that going to do to the temperature on the surface of the Earth? So the star's mass is going to remain at 1, distance is going to remain at 1, planet's bond albedo is going to remain at 1. The only thing we're going to change is the greenhouse effect. We're going to take to 2. So if we come over to our summary page and we set our greenhouse effect to 2, hit results, and once again, please write down the temperature given in Fahrenheit and the temperature produced in Celsius. And then I'm going to ask you for question 3 to calculate the difference in temperature between the values you calculated for question 1 and question 2. And you're going to give your answer in both Celsius and Fahrenheit. So you're going to take your value in Fahrenheit from question 2 and subtract your value in Fahrenheit from question 1, and you're going to do the same for the Celsius values. So for question 4, the average temperature for Antarctica is minus 12.3 Celsius, and for the Arctic it's about minus 10 Celsius. So what will the temperature increase you calculated for question 3 mean for our polar ice caps? So if the difference between your answer to question 2 and your answer for question 1 exceeds these values, so if it's, for instance, is let's say 13 Celsius, well, obviously that means that if you increase by 13 Celsius, that's going to take you above freezing in the Arctic, and it's going to take you above freezing in the Antarctic. And so then you have to wonder yourself, well, once you get above 0, what's going to happen to all that ice? And so you can probably write your answer based on that. So now for question 5, we are going to look at a slightly more extreme situation. So just for interest's sake, we're going to think about what's going to happen towards the end of the sun's life. So we know that our star is not big enough to go supernova, but we do know that when it gets towards the end of its life, it is going to swell in size and it's going to become a red giant. And so as it swells in size, although the star's mass isn't changing, its total volume, its diameter, is going to increase. So the surface of the sun is going to start moving out. It's going to envelop Mercury and destroy Mercury. It's going to do the same to Venus. And in all likelihood, it probably will also envelop and destroy the Earth. But there is a chance the Earth might just survive. So for question 5, what we're going to do is we're going to model what will happen in the event that the sun starts to expand into its red giant phase and the Earth does not get destroyed. So the star's mass is going to stay at 1 because the sun hasn't actually gained or lost any mass at this point. It's just spreading it out throughout a greater volume. We're also going to substantially decrease the distance between the Earth and the sun. So we're going to take it to 0.05 AU. So that's with the Earth very, very close to the sun. We're also going to decrease the bond albedo to 14. Okay, so we are suggesting that at this point, far less of the solar radiation is going to be reflected back into space. And this is obviously going to be a reflection of the fact that the Earth's surface is going to be naturally darkened by this sheer huge quantities of solar particles, solar wind that's going to be thrown onto the Earth's surface, which is going to darken the color. At the same time, bearing in mind the Earth is going to be so close to the sun, the Earth's atmosphere will literally be ripped off the planet. It will be blown away by the extreme solar winds coming off this red giant star. And so we can assume the Earth's greenhouse effect is going to be 0 because we will have no atmosphere. So that also goes some way to explaining why the bond albedo is dropping. because as there's no atmosphere, all those charged solar particles can go smashing into the Earth's surface, and they're going to cause it to become darker in color. So once again, you're going to go to the surface temperature calculator, going to put in the star's mass at 1, distance at 0.05, bond albedo is now 14, and the greenhouse effect is 0. And once again, you're going to get your value for the surface temperature in Fahrenheit and Celsius. So for question 6, it's going to ask you, what is this decrease in distance between the Earth and the Sun going to mean for the Earth's crust? So we need to answer that by going back to these tables here. And it's this table here which is the important one, because this covers the melting point for dry granite and basalt. Remember, we're talking about the Earth's surface when the atmosphere is being stripped away and when it's being blasted by huge amounts of solar radiation. So the granite on the surface is going to be pretty dry, not going to be a huge amount of water. So when we're talking about what's going to happen to the Earth's surface during this time period, well, we're going to start thinking about, is it going to melt? Is the temperature going to get above the melting point for either granite or basalt? If it gets above the melting point for granite, obviously the continental crust is going to start melting. If it gets above the melting point for basalt, the oceanic crust is going to start melting. So your answer to question 5 is going to be used for question 6, and essentially compare the values that you get to the melting points for dry granite and basalt and work out, will the crust start melting, yes or no? And if it does start melting, which parts of the crust will melt? Would it just be the continental crust melting, or would it be the continental and the oceanic crust melting? So after we've completed that, we are going to move on to question 7. And so in question 7, what we're going to do is we're going to imagine that the Earth's outer core has fully solidified. Now, this is the situation where Mars finds itself. So obviously, the planet of Mars, just like Earth, did used to have a liquid outer core. And of course, just like Earth, the convection of this liquid outer iron nickel core led to the formation of a magnetic field that will have protected the surface of Mars from the solar wind. Now, the problem is that eventually this outer core went and cooled and solidified as the interior of Mars began to lose more and more heat, and eventually the entire interior pretty much solidified. Now, this obviously means once the outer core solidifies, obviously all of that convection, which produces the magnetic field, stops. And so you then end up with a situation where your magnetic field is gone. There's nothing protecting your atmosphere from the solar wind coming off the sun. And so the solar wind begins to degrade your atmosphere. And eventually you end up with the point where Mars is now, where it has a very thin, very tenuous atmosphere, which it's just holding on to. But, you know, in the past, when it had this magnetic field, its atmosphere would have been considerably thicker and way more Earth-like. So anyway, let's imagine what would happen if the Earth's outer core completely solidified. Well, once again, star mass of 1, distance of 1, bond albedo of 29, greenhouse effect of 0. And so, all right, greenhouse effect is gone. What would that do to the temperature on the Earth's surface? So for question 8, you're going to take your answer from question 7 and you're going to compare it to your answer from question number 1. And you're going to calculate how much additional heat does the Earth's atmosphere actually help us to retain. And you're going to give your values in Celsius and Fahrenheit. So once that's been completed, you are going to move on to question 9. So for question 9, we're going to start thinking about the idea of snowball Earth. So geologic evidence suggests that towards the end of the Proterozoic, about 720 million years ago, the Earth appears to have gone through a period of time between about 720 million years ago and 540 million years ago, where there were 4 large-scale global glacial events. Now, the largest of these events appears to have occurred sometime between about 720 million years ago and about 650 million years ago. And it's been suggested that based on the evidence that's been observed for rocks of that age, that a significant or possibly all of the Earth's surface was covered in an ice sheet. And so this event is referred to as Snowball Earth, and it's actually addressed in great detail in the Proterozoic portion of the Precambrian geology lecture. So we are going to be thinking about what kind of conditions you would need to have achieved in order to allow this runaway glaciation to begin. And so to begin with, we obviously need to calculate changes in bond albedo associated with changing ratios of land and ocean versus ice. So if you look at the table that we have here, you can see that we have the fraction of land plus ocean. So 1 is 100%, so that would be the planet of the surface of Earth would be nothing but ocean and exposed continental crust. And it goes all the way down to 0, which is 0% land and ocean. That in that case, that would be the Earth's surface is just a solid layer of ice. There is no ocean or continental crust exposed. Then we have the bond albedo for the land plus the oceans, which is 29. We're going to skip column 3 right now. We're going to move to column 4. So for column 4, we have the fraction of ice. So obviously, if we have 100% land plus ocean, the fraction of ice on the surface of the Earth is going to be 0 because there can't be any ice because it's all land and sea. In contrast, once we are down to 50% land and sea, well, obviously at that point, 50% of the Earth's surface is going to be ice. In the case of ice itself, it obviously has a much higher bond albedo, so it's going to reflect more solar radiation back into space. And so the bond albedo is set at 75. And so what you can work out is as you begin to lose exposed crust or exposed continental crust and exposed ocean, and you replace it with ice, that's obviously going to lead to more solar radiation being reflected back into space because the bond albedo is going to start higher. What we're going to start doing is we're going to start calculating the portion of the total albedo for the fraction of land plus ocean. So the example calculation here is given for a situation where the Earth's surface is 80% land plus ocean and 20% ice. So for the total portion of the bond albedo for land plus ocean, we are going to take the fact that it is 80% land plus ocean and the bond albedo is 29, and we're going to do 0.8 multiplied by 29, and that's going to give us 23.2. We're then going to do the ice fraction, so that's 20%, so 0.2, and we're going to multiply that by 75, which is the bond albedo, and that's going to give us a value of 15. And then finally, for column 7, we are going to produce the total bond albedo for the Earth if it is 80% continental crust and ocean plus 20% ice. And so to do that, we're simply going to add together 23.2 and 15, and that's going to give us a total bond albedo of 38.2, which is slightly higher than we have now. And that's not surprising because 20% ice coverage is higher than we have now. And so if the Earth's surface today was to be covered by 20% ice, obviously that's going to drive up the bond albedo because that ice is going to be reflecting more solar radiation back into space. Okay, so you're going to complete the rest of the table. So for instance, for let's say 50-50, so 50% land plus ocean and 50% ice, you're going to be doing 0.5 multiplied by 29 and 0.5 multiplied by 75, and then you're going to add the values from column 3 and column 6 together to give you your total bond albedo. And so you're going to do that for each of these ratios. Now, once you've done that, you are then going to move on to question 10. So question 10 is going to ask you to calculate global temperatures for each of the land plus ocean versus ice ratios using the bond albedos that you calculated in question 9 here. So these are going to be using the values from column 7. So what are you going to do? Well, for the sun's mass, you're going to keep it at 1. You're going to keep the distance between the Earth and the sun at 1.25. So we've increased the distance slightly, and this is because we are dealing with a sun that's still a little less bright than it is now. So by increasing the distance, we are slightly decreasing the amount of solar energy that the planet Earth would be receiving. And we're going to put the greenhouse effect at 2.25 because we know the greenhouse effect in the Proterozoic would have been stronger than the present day. So what you're going to do is you're going to put sun's mass of 1, distance of 1.25, and a greenhouse effect of 2.25, and you're not going to change those for the rest of question 10. The only value you're going to be changing is bond albedo, and those values are going to be based on the total bond albedo that you calculated in column 7. Okay, so for a ratio of 100% land and ocean to 0% ice, you are going to take the total bond albedo, which is 29, and you're going to put 29 in, and you're going to do your calculation. So you're going to have 1, you're going to have 1.25. Didn't want to do that again. It's going to be 1.5, and our greenhouse effect is going to be 2. Okay, and so for this ratio here, you're going to put in these values. You're going to ask it to calculate your result. You're going to get the temperature Fahrenheit and the temperature in Celsius. And then finally, you are going to tell me what would be the state of water on the Earth's surface. And to keep things simple, we are dealing with fresh water here. We are not talking about salt water. We're talking about fresh water. And so we know that the freezing point of fresh water is 0 degrees Celsius. So if your value in this column is above 0, you know that surface water will remain liquid. If it drops below 0, you know the surface water will be solid. So you're going to work your way down the different ratios, and you're going to use the bond albedo that you calculated for each ratio, and you're going to put it in to the calculator. So that's the only value you're going to change. And for each of the ratios, you're going to calculate the surface temperature in Fahrenheit, Celsius, and then you're going to tell me whether the water on the Earth's surface would be liquid or solid based on those values. So once you've done that, you are going to move on to question 11. So for question 11, at present the Earth's surface is covered by approximately 3% ice. But during the last ice age, that value increased to about 10%. So using the values you have calculated above, so for question 10, would 10% ice coverage have been enough to start a runaway glaciation in the Proterozoic? So we're going to look at 10%. So that's going to be 10% ice, 90% land and ocean. And then you're going to look at your Celsius value and you're going to see, is it above or below 0? All right, if it's above 0, then no, the surface of the Earth would have retained a significant amount of liquid water. If, however, it's below 0, surface water would have been freezing, and so in that case, a runaway glaciation like we saw in the Proterozoic would have been possible. So finally, for part 1, we have question 12. So using the values for 100% ice coverage, so that's going to be these values down here, how strong would the greenhouse effect have to have been to get temperatures back above 0 degrees Celsius? So one of the things that we know about Snowball Earth is, obviously, the Earth's surface is not still a giant ice cube. So that brings about the question of, well, how did it stop? What caused the ice to melt? And so the only logical explanation is that the Earth's greenhouse effect throughout the Proterozoic steadily became stronger again. and this will have led to the greenhouse effect becoming more potent, more heat being retained on, in the Earth's atmosphere and on the Earth's surface, and that will eventually get to the point where the Earth's surface is warm enough to start the ice melting. And so what you're going to do is you are simply going to take the conditions that you have for 100% ice coverage, and you're going to start increasing the greenhouse value for the planet temperature calculator. Okay, so you are going to keep the sun's mass at 1. You're going to keep the distance at 1.25, and you are going to keep your Bond albedo at whatever value you calculated here. And so the variable in this case will be the greenhouse effect. And so for those 3 values, so you're going to start off with the greenhouse effect at 1. You're going to see what will the surface temperature be. Then you're going to take the greenhouse effect at 2. What would the surface temperature be? Are you above or below 0? Then you're going to go to greenhouse effect level of 3. Would the Earth's surface be above or below 0? And eventually you are going to increase the greenhouse effect to the point where you make it above 0. And this is the point at which your ice would begin melting. And so what you're going to do is you're simply going to write the whole number. So your greenhouse effect could be, I don't know, 5, it could be 10, it could be 15. You're just going to write the number here, but that's the strength of the greenhouse effect required to begin melting the ice if you had 100% ice coverage. So this is a good point to stop this video. So please get up, have a walk around, get yourself a glass of water, take a few minutes to decompress, and then return for part 3 of this video. Thank you.